Hello, everybody. My name is Jose. I'm indeed a PhD student from the VUB, and I will be talking today about DynaMine version 2, a software that we are developing. And by we, I mean also me and also my coworker, Joel, which should have been with me today giving the talk, but he's been ill for a week. So, well, I'll be giving a presentation on behalf of both of us. So, when we talk about DynaMine, the first thing we need to do is talk about protein dynamics and like the background behind it. It's like, for me, a protein is like I see the protein as the worker of the cell, and when you have a worker that is tied, you don't see how it moves. You can have some idea of what he or she might be doing, but you don't know it as much as when you are seeing it in movement, doing it action. This is also the same with proteins. Just by looking at the structure, you can obtain a lot of information from it, but you're still not getting the full picture. And however, most of the structures that we have right now are static, and we cannot show the dynamics that they have. And it's very represented when losing a lot of information. We wanted to tackle this, and our journey begins in 2013 when the original DynaMine was released. Original DynaMine was a software for which you were putting the protein sequence, and as an output, you were having a prediction of the backbone dynamics. The training data that was used to make this predictor was backbone order calculation that was calculated from chemical shift data. This is a proxy to backbone dynamics, although it's not directly backbone dynamics. And the training algorithm that was used, the learning algorithm, was 20 linear regressions, so one per amino acid, which effectively reduces the training data 20-fold, and only because of the limitations of the algorithm can only account for linear relationships. So this is what DynaMine was doing. You just get a protein, it does its thing, and it returns protein backbone dynamic. And this DynaMine has been trained with only chemical shift data. And for DynaMine 2, what we're doing is we're including also molecular dynamics simulation data, which we expect will give more accurate predictions. To generate this molecular dynamics data, we first got a set of 100 proteins. Some of them were structured, some others half disordered and disordered. Then we run 100 simulations, one per protein in GROMACS, for 100 nanoseconds with time steps of 1,000 picoseconds using the force field CHARM36M. Then, for each amino acid at each time step, we measured the phi and psi angles that it had. In addition to this, we also had chemical shift data for these 100 proteins. So what we did with this chemical shift data is we converted it to one value, like an encoding of one value with ShiftCrypt, which is a software we developed in our lab. And from this ShiftCrypt value, we defined 5 regions. The first one is core helix, so like regions that are very clearly a helix. They have surrounding helix, which is it's mostly a helix, but not quite as the manual would say. Same goes for beta. You have core beta and surrounding beta, and also finally coil. Then we saw the phi and psi angles from these regions, and we mapped them into Ramachandran plot, and that way we define different regions according to these 5 classifications that we had defined. So when we get the coordinates for the phi and psi angles and we put them into our Ramachandran plot, we can derive how likely it is this amino acid to be found in a core helix, surrounding helix, etc. And from how much this amino acid moves in this plot with a time step, we can deduce the dynamic parameter. In this case, this amino acid has been only like not moving that much, pretty much in the same region, therefore it has a low dynamic parameter. However, if you have an amino acid here in purple that has been moving around the region a lot, then it has a very high dynamic parameter. In total, we have 6 labels per protein and residue. And just to illustrate how these propensities and dynamic parameters look, For instance, if we look at like the core helix propensity of a protein, in the x-axis we have the position, the amino acid position, and in the y we can see how likely this amino acid is to be in the getting the core helix conformation. And also for this same protein, we are showing here how dynamic this protein is. So the higher the value, the more you would expect this region to move. With these 6 labels that we have calculated, we train our neural network. For this neural network, we start again with an amino acid sequence. Then we put this amino acid sequence into an embedding layer. This embedding layer transforms our protein into 6, so each amino acid into a 6-dimensional vector. And this vector is trainable. And once it has been training, actually, you can see that it clusters amino acids that have similar properties. Then, with this representation we get for each amino acid for the whole sequence, we move it into a recurrent layers using a gated recurrent unit. What we're doing with this layer is that if you have an amino acid in certain position, it's surrounded by other amino acids, and the properties of this amino acid surrounding it might affect the properties of this amino acid itself. With a recurrent cell that goes both sides so it goes left to right and right to left, you calculate the hidden dimensions of this amino acid, which carries information about the neighboring amino acids. And you also do that for all the amino acids in the protein. When you have this representation, you move it to fully connected layers, which is a normal neural network that, with its weights and biases, that is trying to optimize for an output. You obtain the same 6 labels that we talked about before, and here you calculate the loss and backpropagate the error to get the best network possible. When you're training a neural network, the first thing you want to check is if your network is complex enough to represent your problem. To do so, you want to see if you can at least overfit your result. According to Wikipedia, an overfitted model is a statistical model that contains more parameters that can be justified by the data. So if we are getting our model is overfitting, we're going to see a perfect overlap of the ground truth and the predicted values. So with this, when we check 250 epochs on the training set, we just check a protein for which we have only predicted the dynamic parameter, we see that it hasn't overfitted yet. Blue should be aligned with the orange, but it's not quite there yet. However, when we go to the 1,000 epochs, we can see that this overlap has been reached. This means that our model at least is complex enough to represent our problem. So overfit check. But this is only a dynamic parameter, the backbone dynamics. We talked about 6 labels. So we also try to predict the 6 labels, and also reaching 1,000 epochs in the training set, we saw that it had overfitted, but not as much as before. This is most likely due to like when you have more parameters, it might take longer to converge into perfect overfit, or maybe the model is not complex enough anymore to overfit the 6 parameters. But we don't care about it, because if we had this result for the test set, we will be extremely happy. This has certainly included some regularization into our model, because now we can see that the overfit has been reduced and the model is generalizing slightly better. But of course, models are only as good as they perform in the test set. So when we look at the test set at 250 epochs, because this is the moment in which the test set performed the best, we can see that there's some signals that are captured, and some others are far from perfect, are off. But I also see that some of them are interestingly off, because when I look at these figures, I see especially in alpha and surrounding alpha, I see a region that really annoys me, first annoyed me a lot. Then the more I started looking at it, I saw that around amino acid 80, there is a peak in alpha that matches a valley in surrounding alpha, and the other way around, a valley in alpha that matches a peak in surrounding alpha. And if you also look at the ground truth for the propensity of alpha, you can see that it should be very, very high, whereas for surrounding alpha should be well, non-existent. This region shouldn't be in surrounding alpha. And what we're seeing is like there seems to be some like these two alpha and surrounding alpha, when put together, are describing almost, not perfectly, I wouldn't say that, but like are describing much better alpha. So there seems to be some leakage between surrounding conformational states, and that for me is very interesting, because if the error we're having is explained by the biophysical conformation that is next to it, it feels like our model is really understanding something from the biophysical point of view. So this really excited me when I saw it. With this being said, we actually want to have a good predictor, so we are continuing working on it. And to get a better prediction, a better test prediction, we need to keep regularizing. What they have done so far is adding multitask. So in this case, we are, instead of one parameter would be the backbone dynamics, we're also predicting all the conformational states. And this has already helped. And then the things that we are working on, and we have been working but still not ready, is we are reducing the complexity of the model to try explain it with less parameters to prevent overfit. Well, all this is to prevent overfit, actually. So we are reducing a number of fully connected layers and neurons. We're doing, in the very similar manner, we're doing the same with the recurrent layers. So we're reducing number of hidden dimensions or hidden layers, including dropouts, which basically what it does is it blinds some of the neurons while training, like alternatively, and that way you also, it improves generalization. And we are exploring the use of custom weights for each parameter. So when we calculate the loss, some of these parameters will have more importance than others. Also, we are testing one regularization, and please, we're open for suggestions. Anything that could come from you is very, very welcome. But from all of this, especially keeping into account the previous figure, I'm very now keen on testing very different custom weights and see there's also some ways of changing them dynamically, because there seems to be some tweaking we could do there with neighboring conformations. And also, in addition to this, we also want to improve our model by including chemical shift data, because we've got, I think, a couple of thousand sequences that could really help improve our training. And we will do this by calculating the shift crypt index of these sequences, which, as a reminder before we said, is a single encoded value of the chemical shift data of the protein. And we will use this shift crypt index to, we predict it, to try and move the network into a more general state that would predict the test set better. So in conclusion, DynaMine 2 features a new definition of dynamics, which we believe is closer to reality. Now, with neural networks, we can allow nonlinear relationships in DynaMine 2, as we couldn't in DynaMine 1. With the recurrent layers, we can include information from the surrounding amino acids used for the predictions. And we have seen from the results that there's clearly a signal, although some of it is off. But it's interestingly off, because at least it goes to neighboring conformational states. And our future work is focused on really pushing regularization and inclusion of chemical shift data, which might actually regularize it. With this, I would like to thank all my affiliation and my group, and very, very special thanks to Joel, who couldn't be here and has been working with me and generated all the molecular dynamics data that we have been talking about. That's it. Thank you very much.
Great. Thank you very much for this presentation. Again, very, very nice, very interesting. I see I have here a question from Nicolina. She asks, which criteria did you use to select the initial 100 protein structures for MD? And do you think the method would benefit from a larger set of structure used at that step?
Well, so this, the selection of proteins and running simulations was my co-worker's job, but I actually was in some of the discussions on this. The criteria we had is we also needed to have chemical shift data, experimental chemical shift data, so that we could do the shift group. And then it was, it needed to have a structure also, of course, because we need to run molecular dynamics. I guess, I don't remember that there will be some criteria on how good the structure is, although maybe not so much, because I think the big criteria here to follow was, do we have a nice variety of ordered, disordered, semi-disordered proteins? That was the key thing, that our model wasn't skewed towards only disorder or only ordered. Yes, that I think was the main thing, but was some time ago already, and it wasn't my thing. So I think this is as much as I can tell you without lying on anything.
Okay, great.
Yeah,
no, that's already good.
Yeah.
I want to remind the audience, if you have questions, there is the question tab where you can type in your question and send them. Meanwhile, I had also a few questions, namely, well, maybe again, discussing about the type of proteins, but I mean, during your model, during your embedding, maybe I missed something, but I was wondering, do you also include, I don't know, the type of protein it's coming from? Is it like, I don't know, membrane? Is the sequence coming from membrane protein or only secreted proteins? And do you think your model could be adapted, because I guess afterwards could be adapted to any sequence that can be supplied?
I got a bit confused because you brought up the embeddings.
Sorry, maybe. No, just I was wondering if in your model you could also include additional metadata on the proteins. That's maybe more the focus question I want to ask.
Okay, so this is generally very easy to include from the algorithmical point of view. It's easy to just put it, and if it works, it worked. Otherwise, the whole network is just going to downweight it, and it's not going to be used at all. But we are trying to get away from it and going to a full agnostic, full agnostic one, because there's quite some papers already showing how not using humanly classified tags usually work better, because like the information is still there, and if you, like in this case, maybe we don't have enough sequences to extract as much information as you could get, but there's already quite some papers showing that only from the sequence you can already extract properties like secondary structure and many other things. And there's even comparisons that have shown that very often even the one hot encoding, not giving any other information, outperforms using classifications done by humans. Okay. So it's something that we consider at some point, and we are not close to it. It's especially because we have a lot of contacts with people that have databases, so that's a nice thing. But we are also, I think, for now trying to just keep it as agnostic as possible. And if something is derived from there, it's not dependent on someone measuring everything correctly later in the lab or assigning it correctly. So this way, if you the good thing about this, by the way, is that you just need a sequence. Yeah. You are also a new person that, like a bioengineer, that is modifying your sequence and wants to see how this will affect your final protein. You can just put it there and see what would happen. Yeah. Like maybe like how precise it would be at the end. You need to validate it, of course, but it already, like that way you are really reducing the bias towards that.
Yeah, great. That makes a lot of sense indeed. Yeah, nice.
Yeah, actually, I just see that there's I haven't replied to answer half of the question of yeah, Nicolina, sorry. Yeah, indeed, the more the merrier. Like we keep running simulations actually, and just but for the results that we had very nicely shown for this presentation, we did it on the first 100. No, we keep doing more. I think we're doing roughly 10 proteins more per week, because we have a few nice GPU computers that we can just shoot it into. But yeah, the more the merrier, certainly. That will improve as we get more proteins.
Okay, great.